Hi everyone, I'm Mert, PhD candidate at University of Illinois. I'd like to present my work on extremely large X-ray image reconstruction. I have been leading this project since I was a Givens Associate at Argonne National Laboratory in the summer of 2018. Here is my 20 minutes presentation outline. First, I'll explain you the motivation of this work. Second, I will introduce you the memory-centric XCT algorithm. Third, I'll go through the proposed optimizations in our paper, specifically target multi-GPU node architecture. Then I will go through some highlight results on Summit supercomputer, and finally, I will conclude my talk with a few remarks. X-rays enable scientific discoveries by providing images of large samples without cutting or destroying them. Large scans with high-energy X-ray beam can only be obtained at particle accelerators such as synchrotron light sources. Each light source has multiple beamlines with advanced instrumentation for domain scientists to scan their samples along with their science. These advanced light sources are constantly improving by recent and future upgrades. The upgrades provide thousands of times more brilliant X-ray beams for scanning larger objects. Moreover, the upcoming instrumentation will enable imaging with sub-10 nanometer resolution. This will be a game changer for many applications, but the image production will be limited by how fast we can process the measurement data. If we look at historical trends, X-ray brilliance triples every 18 months, and the data to process increases with a direct proportion. However, the processing speed only doubles in the meantime, according to Moore's law. With the emerging performance gap between the light sources and processors, large-scale image reconstruction has already been infeasible on modest workstations. To keep the science up with the gap, it is a must to develop high-performance codes to run processors efficiently and scalable algorithms to employ thousands of them in parallel. Large-scale image reconstruction is unilaterally formulated as an optimization problem because it's common to have imperfect measurements due to experimental constraints. These imperfections involve noisy, blurry, and incomplete measurements, which cannot be handled by direct or analytical methods. Therefore, the problem has to be solved iteratively. The objective functional to be minimized consists data mismatch and regularization terms. In data mismatch term, matrix A corresponds to the forward model, which simulates the X-ray propagation through the 3D sample. On the other hand, vector B corresponds to the measurement, which also can be stored as a 3D data cube. That is, many 2D projections of the sample are recorded by a CCD camera. Each shot is taken from a different rotation angle, and K of these shots are stacked together to produce the measurement data cube. Similarly, the 3D image can be obtained by stacking many 2D images, each of which is called a tomogram. Each tomogram can be reconstructed independently by a single horizontal slice of the measurement, which is called a sinogram. There are two main expansive operations in each iteration we need to perform: projection and back projection. To understand, let's take a look at the computations. The projection performs ray tracing on the voxels in a tomogram, which is a gather operation. The same applies to the back projection, but with a scatter operation. A compute-centric approach performs these on the fly with expansive nested loops and conditionals, which are not vectorizable. Moreover, the same expansive computations are performed for each iteration from scratch. On the other hand, the memory-centric approach implements these operations as explicit sparse matrix multiplications, with the expense of an additional memory complexity. Nevertheless, we have shown in our SC19 paper that it is 50 times faster when optimized. The memory-centric approach reduces inefficient computation so much that the performance becomes limited by the memory subsystem. So what are those limitations? First, the memory accesses are irregular, where cache lines are not efficiently utilized. Second, back projection yields serialization due to race conditions. The second problem is solved by a scatter-to-gather transformation, where the irregular data accesses are read-only but on the sinogram domain. This is obtained by a transposition of the projection matrix and storing it as the back projection matrix. It is computationally efficient, but it doubles the memory footprint of the application. These matrices have terabyte-scale memory footprint for large problems, and therefore it takes a supercomputer to solve them. As an example, these numbers are taken from the mouse brain dataset in our paper. Here, the projection matrix is extremely sparse, and so the back projection matrix. Nevertheless, they have as large memory footprint as of the dense matrices. Each column of these dense matrices correspond to a single slice of the 3D input and output datasets. Many prior work follows a memory-centric approach, but many of them also involve inefficiencies. We have tackled these inefficiencies in our SC19 paper by removing any irregular accesses to high latency memory, race conditions that yield serialization, or memory duplication with unnecessary communications. We have also proposed a novel sparse matrix tiling that maximizes device throughput. In this paper, we extend our previous optimizations for 3D datasets, optimize the GPU performance further, and focus on the communication bottleneck. Furthermore, we battle test our application by scaling out on Summit supercomputer. As an example, our paper demonstrates image reconstruction at unprecedented scale in terms of dataset size, number of devices, and computational throughput. But most importantly, what makes our work unique is that it targets multi-GPU node architecture to tackle the communication bottleneck. This makes our work future-proof because the next wave of DOE exascale supercomputers will have multi-GPU node architecture with no exception. We observe that when scaled out with sufficiently high device throughput, communications dominate the end-to-end reconstruction time. This is also reported commonly by previous work. In this work, we exploit the high bandwidth interconnect within nodes to reduce the communication volume between nodes by 64% with no approximation. I will present the optimizations in our paper in the following order. First, I will explain our partitioning strategy, which is designed for multi-GPU nodes. Second, I will go through the optimizations for accelerating sparse operations on GPUs. We propose a novel shared memory tiling and register tiling with mixed precision implementation. Third, I will explain the communication bottleneck and how we tackle it with hierarchical communications. I will also mention how we hide communications further in the batch processing pipeline. These optimizations go well with both large and small datasets. For example, reconstruction of the shale sample takes only 42 seconds on 4 nodes of Summit, including disk I/O. It is not easy to make an apple-to-apple comparison with previous work, either because they perform different iterations or their benchmark datasets are proprietary. But just to give you an idea, the table makes a rough comparison. Thanks to the efficient implementation, we can fit this problem into 24 GPUs within 320 gigabytes of memory footprint. A related work from last year solves a similar problem on 8,640 KNLs within 124 terabyte of memory footprint, approximately within the same reconstruction time. To provide a benchmarking for future work, we open source our code with some small to medium datasets, including this one. This example shows how we partition the measurement and reconstruction cubes among 3x4 processor grid. Here, each processor corresponds to a GPU. The vertical partitions employ batch parallelism, and horizontal partitions employ data parallelism. If we look at the same picture from an algebraic perspective, the sparse matrix is partitioned across every 4 data processors, and each partition is duplicated across 3 batch processors. When it comes to the dense matrices, they are perfectly partitioned with no duplication. For the projection operation, the sparse matrix is partially multiplied at the sender processors in parallel, and then a communication is performed to reduce the partial results into the total results at the receivers. Note that each processor is both sender and receiver. All of these are transposed for the back projection operation. In both cases, communications are sparse and are totally dependent on the sparsity pattern of projection matrix. We inspect the sparsity pattern during pre-processing and construct the communication data structures accordingly before the iterative solution. As a result, data parallelism reduces the per process memory footprint but comes with communications. On the other hand, batch parallelism duplicates the sparse matrix for employing more processors in an embarrassingly parallel fashion. We use this observation for topology-aware rank assignment. That is, we place data processors in the same node as much as possible just to exploit the high bandwidth interconnect better. The optimum balance between the data and batch parallelization has to be found out by the user, since it depends on the application memory, processor memory, and the number of GPUs per node. For data parallelization, we implement a Hilbert ordering domain decomposition. This fills the tomogram and sinogram data in their respective 2D domains. The provided data locality by the Hilbert curve is greater than the Cartesian curve. This reshuffles the rows and columns of projection matrix where non-zeros are localized. This is a fundamental design choice that our application makes, which helps GPU throughput and optimizes communications across GPUs. Remember that the communications depends on the sparsity pattern. The locality provided by Hilbert ordering promotes communications across GPUs within the same node and less communications across nodes. With the reordering, the partitioning is obtained simply by dividing the consecutive data equally across GPUs and then across thread blocks. Here, each thread block operates on a 3D partition. For sparse matrix tiling, we inspect memory access patterns, which is governed by the X-ray propagation geometry, and then build the data structures that maps GPU global memory to on-chip shared memory. We do this in the pre-processing stage by coloring the access footprint of each thread block. For example, the data painted in blue is accessed to compute the sinogram partition highlighted in blue for projection. Similarly, the data painted in red is accessed to compute the tomogram partition highlighted in red for back projection. This is performed for each thread block where the irregularly accessed data is loaded into the shared memory once and then accessed multiple times by multiple threads. This provides data reuse from fast on-chip shared memory and reduces the high latency global memory accesses to a great extent. For large geometries, however, the memory access footprint per block is so large that it doesn't fit into 96 kilobytes shared memory capacity of GPUs. To overcome this problem, we developed a multi-staging algorithm where irregular memory accesses are performed with multiple shared memory stagings. In this case, projection and back projection perform irregular accesses with 4 and 3 stages respectively. In order to load more data within the shared memory, we use mixed precision. Data is stored and communicated in half precision, but all fused multiply adds are performed with single precision arithmetic by in-core conversions. Then the result is written back in half precision for communication. This reduces the memory and communication footprints and increases the GPU throughput while avoiding any half precision arithmetic. To overcome the low range and granularity of half precision, we implement an adaptive normalization and denormalization technique, which is explained in detail in our paper. The last optimization we make is reusing the sparse matrix from registers. Each thread computes multiple outputs in the Y dimension, which we call mini-batching in the paper. This increases the arithmetic intensity and saves memory bandwidth where GPU performs more computations per byte from global memory. But it puts register pressure on the streaming multiprocessors, which is not good if it's used too much. To find an optimal value, we try different minibyte sizes and look at the roofline analysis. Reduced precision naturally increases the arithmetic intensity, which is good. We observe that the performance is bounded well by the memory bandwidth for small minibyte sizes as expected. We also observe that the horizontal roofline is an effect of excessive register pressure, where the GPU hardware tries too hard to arrange its valuable register resource. Nevertheless, we utilize about 40% of theoretical GPU throughput with these optimizations. Our evaluation shows that this is 2.4 times faster than NVIDIA's cuSparse library. This brings us to our most important and novel optimization, and the main theme of this work, the hierarchical communications. The plot shows the breakdown of end-to-end reconstruction times for the large charcoal dataset. We timed reconstructions with double, single, and mixed precisions within 128 nodes. Since lower precision yields a smaller memory footprint, it is easier to fit the problem into a smaller number of nodes. At this point, we unemploy data parallelization and replace it with batch parallelization to minimize communications. Lower precision naturally reduces the communication volume further. Nevertheless, after GPU kernel optimizations are applied, the reconstructions are dominated by communication time. To address, we develop hierarchical communications, which reduces this bottleneck by 50% by exploiting the multi-GPU node architecture. To understand, the figure shows partitioning of tomogram and sinogram domains across 24 GPUs in accordance with the Hilbert ordering. We highlight GPUs 12, 13, and 14 on the left, which are located in the same socket and are fully connected with the high bandwidth NV links. In projection, each GPU computes its partial result and then scatters it among the receiver GPUs on the right in accordance with the partial data footprints on the sinogram domain. Then, the receiver GPUs finds the total result by simply adding the overlapping partial results coming from standard GPUs. In this example, GPU 22 sums the overlapping sinogram data coming from GPUs 12, 13, and 14. A direct communication of the partial data yields a sparse communication matrix. For large problems, most of these communications go through the slow interconnect between nodes, which constitutes the bottleneck. The hierarchical communications reduces the overlap data locally at the standard GPUs in the same socket, and then communicates the reduced data across nodes. This requires an additional communications within sockets, but with less communications across nodes. In this example, GPU 13 is responsible to reduce data for the receivers on the right, highlighted with the same color. To do that, it collects the partial data from GPUs 12, 13, and 14, and then reduces the overlapping portions according to their original communication footprints. As a result, the data at receivers is already reduced locally within the sender socket. The extra communications and reductions within sockets are so fast that the overhead pays well, because the reduced data going out of sockets is 43% less than the original data produced by individual GPUs. With this idea, we build a three-level communication and data reduction hierarchy. First, a set of local communications is performed among every three GPUs within the same socket. This yields a block diagonal communication matrix with 3 by 3 blocks. After the socket level reduction, the total communication volume is reduced by 43%. Then a second set of local communications is performed among every 6 GPUs within the same node. After node level reduction, the volume is reduced further by 36%. Finally, the global communications are performed between nodes with a total of 64% reduced data. Details for efficient implementation of this are given in our paper. Lastly, we pipeline the batch processing to hide communication overhead further. This takes full advantage of the 3D nature of data. The pipeline overlaps the global communications across nodes with the local GPU computations and communication within nodes. This overlapping strategy brings an extra 21 to 29% saving for the end-to-end execution time. To demonstrate a full-scale reconstruction on Summit, we use the heroic mouse brain dataset that is collected at Advanced Photon Source of Argonne. With all optimizations on, it fits into a minimum number of 128 nodes with data parallelism. Then we strong scale up to 4096 nodes with batch parallelism. The total number of 24,576 GPUs reached 65.4 petaflops, which corresponds to 34% of Summit's theoretical peak performance. We also observe that the reconstruction is dominated by communication and I/O times, although they are optimized. We're in process of further optimization of the I/O time. Nevertheless, with the current implementation, we obtain 3D brain reconstruction within 2.5 minutes. For weak scaling, we start with a synthetic dataset that fits into a single node. Then we double each side of the measurement data cube, which increases the computations by 16 times in each step. The results up to 256 nodes show that the kernel time remains the same thanks to the efficient partitioning strategy. However, the total time is dominated by communication and I/O overheads for large problems. Let me draw the conclusion. First, scientific discoveries with the new wave of light sources will only be enabled by efficient, scalable algorithms such as the one in this work. Second, we develop shared memory tiling and register tiling with mixed precision implementation to maximize GPU throughput for sparse computations. With the high throughput, communication time dominates the end-to-end reconstruction time. Third, to tackle this bottleneck, we propose hierarchical communications for multi-GPU node architecture with an overlapping strategy within the batch processing pipeline. And last, with all these optimizations, this work demonstrates an unprecedented scale image reconstruction in terms of data size, number of GPUs, and peak performance. My PhD thesis in progress formulates the proposed techniques in this paper for general sparse operations on multi-GPU node architecture. We have already generalized these to some extent for a broad class of scientific and AI workloads. Before closing, let me tell you that I support ACM's reproducibility effort and proud to be the leading author of this year's challenge benchmark. To that extent, we open sourced our code and benchmark datasets. For dissemination, we're working with domain scientists to prepare our code for production at DOE laboratories and beyond. We're seeking for a grant to do that. Thank you for your time, and I'm ready to take your questions.